Look up, what you see is a lie, not a cruel one, but a magnificent one. The night sky performs its oldest deception. Solid objects, ancient light, the grand theater of mass and gravity curving through space. We have spent 10,000 years building languages to describe this performance. Physics, mathematics, philosophy, poetry, and every single one of them has chased the same ghost. What is a universe actually made of? Not what it looks like, not how it behaves under our instruments. What is it at the level beneath levels, where the questions run out of floor? The answer, emerging from the strangest corners of modern science, is not matter. It is not energy. It is something so abstract, so counterintuitive, that confronting it directly feels like staring into the event horizon of a conceptual black hole. The universe, at its most fundamental resolution, is made of information. Peel back the atom. Go deeper than the proton, past the quarks, past the quantum foam where spacetime itself becomes granular and uncertain. What you find at the absolute bottom of physical reality is not a substance, it is a distinction, a difference, a yes or a no. Physicists have a word for this primordial binary heartbeat, they call it a bit. And before you dismiss that as a metaphor borrowed from computer science, understand that the science insists otherwise. The bit is not a human invention we imposed on nature. Nature was doing it first. Long before silicon, long before Charles Babbage sketched his first mechanical engine, the cosmos was already encoding itself. State by state, spin by spin in an architecture so elegant and so ruthless that our most sophisticated computers are only faint, clumsy echoes of it. The universe does not merely contain information, the universe computes. This is the idea that changes everything, not the digital cosmos as a metaphor for complexity, not a poetic gesture towards the interconnectedness of all things, but a literal, testable, thermodynamically rigorous claim. Physical reality is a computational substrate, and the laws of physics are its operating system. When an electron chooses a spin orientation, a bit is written. When a photon is absorbed, a register is updated. When two particles collide and scatter, a calculation resolves. The universe is not running a simulation. The universe is a simulation from the inside indistinguishable from ultimate reality, because it is ultimate reality. And once you accept this, once you feel its weight settle into your understanding, every question about physics becomes a question about computation, and every question about computation becomes a question about the deepest nature of existence. We are not observers of a cosmic machine, we are subroutines running inside it. Here is where the abstraction ends and the physics begins. Information is not a ghost, it does not float free of the material world. In some immaculate platonic realm untouched by entropy or friction, every single bit of information, every distinction, every encoded difference between one state and another must live somewhere. It must be instantiated in a physical object, an electron whose spin points up rather than down, a capacitor that holds a charge or does not, a carbon atom in a specific bonding configuration, a photon polarized along one axis rather than the perpendicular. The information is inseparable from its physical host. Change the host and you have not moved the information, you have destroyed it and reborn it elsewhere. And this dependency, this unbreakable marriage between abstract data and physical substance, is the first law of information physics. A bit without a body is a contradiction in terms. Consider what this means concretely. Every hard drive and every server farm on Earth is a landscape of magnetic domains. Billions of microscopic regions where iron atoms have been coaxed into alignment, pointing north or south, encoding 1 or 0. Every memory cell in the device in your pocket holds its bit as a quantum of electric charge trapped inside a floating gate transistor. Your DNA encodes genetic information as a sequence of molecular base pairs, adenine, thymine, cytosine, guanine, 4 symbols that reduce pair by pair to a binary alphabet written in the language of covalent bonds. And the synapses in your brain right now, processing these words, are adjusting the weights of electrochemical connections, each adjustment a physical rearrangement of protein configurations and ion channel states. Thought itself is a physical inscription. Memory is a material sculpture. There is no information without matter holding its shape. This is not philosophy. This is experimentally verified physics with measurable consequences. In 2012, researchers at the University of California, Berkeley, conducted a landmark experiment directly measuring the heat released when a single bit of information was erased from a physical system. The result matched theory to within experimental precision. A bit has a physical cost. Information has weight, not gravitational weight in the familiar sense, but thermodynamic weight, a burden measured in entropy, in entropies, in the irreversible scarring of the universe's energy budget. And here is what makes this profound, rather than merely interesting. If information is physical, if it obeys the laws of thermodynamics, if it can be measured, if it costs energy to manipulate, then information is not a tool we use to describe reality. Information is reality, described in the only language the cosmos speaks fluently. Every fact you have ever learned is a physical mark pressed into the world. In 1961, a young physicist named Rolf Landauer sat down to think. He studied the thermodynamics of computation. He arrived at a strange conclusion. His colleagues initially refused to believe it. Landauer proved there is an asymmetry in information processing. This is a deep structural asymmetry. The universe allows some things for free, but it charges a thermal price for others. This result is called the Landauer principle. It stands as a beautiful and disturbing theorem. The core statement is simple. Consider the logical operation of erasing information. Think of taking a bit and setting it to zero. This act is necessarily irreversible. In physics, irreversibility means only one thing. Heat, the universe bills you, and the bill is paid in fire. To understand what erasure actually means at a physical level, when a bit exists in an unknown state, call it x, which might be 0 or might be 1, the system encoding it occupies one of two possible configurations. The bit has what physicists call one bit of entropy, the information content of a fair coin, the mathematical measure of your ignorance about its state. Now you erase it. You force the system from two possible states down to one known state, 0. You have compressed two possibilities into one certainty, and here is where thermodynamics becomes merciless. The second law demands that entropy cannot decrease in a closed system. You have just reduced the entropy of the information-bearing subsystem. The universe will not allow that reduction to go uncompensated. The entropy must go somewhere. It flows outward into the environment surrounding the physical bit, manifesting as thermal energy, as heat shed irreversibly into the world. Memory costs nothing, forgetting costs everything. The mathematics is precise and unsparing. The minimum energy dissipated when a single bit of information is erased is given by a fundamental law. Energy equals Boltzmann's constant multiplied by the temperature multiplied by the natural logarithm of 2. Here, the constant is the fundamental bridge between the microscopic world of atoms and the macroscopic world of heat. It is equal to approximately 1.38 times 10 to the minus 23rd power joules per Kelvin. The variable T is the absolute temperature of the environment in Kelvin, and the natural logarithm of 2 is the mathematical fingerprint of the binary choice being collapsed. At room temperature roughly 300 Kelvin, this evaluates to approximately 2.87 times 10 to the minus 21st power joules per bit erased. That is a vanishingly small number by human standards, but it is not zero, it is never zero, and in a universe that has been processing information for 13.8 billion years across a volume of 10 to the 80th power particles, the cumulative thermal toll of all that forgetting is a number that staggers the imagination. The Landauer limit is the absolute thermal floor of computation, the lowest possible energy costs that the laws of physics permit for the act of erasure. No engineering innovation, no materials breakthrough, no algorithmic optimization can go below it. It is not a practical limitation waiting to be overcome by future technology. It is a law inscribed in the same mathematical bedrock that forbids perpetual motion and prevents heat from spontaneously flowing from cold to hot. Modern transistors dissipate energy roughly 1 million times above the Landauer limit. We are not close to it yet, but as chips shrink toward atomic scales, as quantum computers begin operating on individual qubits, this floor is approaching. Within decades, engineers will press against it directly, and when they do, they will not be fighting a technical problem. They will be negotiating with thermodynamics itself, with the fundamental tax the universe levies on the act of forgetting. Now sit with the asymmetry, because it is genuinely terrifying. You can read a bit for free, you can copy a bit for free, you can transmit a bit across a fiber optic cable at the speed of light, and the universe extracts no thermodynamic toll for the act of transmission or duplication. Knowledge is cheap, learning is thermodynamically free. The cosmos, in a sense that is not metaphorical, is generous with the act of discovery. But the moment, the precise irreversible moment that you try to delete a bit, to overwrite history, to collapse a record that once existed, the meter starts running, the universe charges you, the payment is heat, and you cannot negotiate, you cannot defer, you cannot find a clever workaround in the logical architecture. The asymmetry between writing and erasing is not a quirk of our current technology, it is a fundamental feature of the universe's accounting system enforced at the level of physical law with zero exceptions. This is why standard digital logic is a thermodynamic catastrophe in miniature. Consider every AND gate, every OR gate, and every NAND or NOR gate in the billions of transistors packed into a modern processor. These are what physicists call logically irreversible operations. They are computational steps where multiple possible input states collapse into a single output state, destroying information in the process. When a two-input AND gate outputs 0, you cannot reconstruct the past. You cannot tell whether the inputs were 0, 0, 0, 1 or 1, 0. That information is gone forever. Three possible histories are compressed into one ambiguous present. The entropy shed in that collapse hits the chip. It warms the air around it, the data center, and the entire planet. Every computation your phone performs, every query your search engine resolves, and every frame your graphics card renders is a cascade of small irreversible erasures. Each one pays Landauer's toll, each one warms the universe by the minimum amount the laws of physics allow. There is a theoretical escape route, and it is as beautiful as it is impractical. In the 1970s, physicist Charles Bennett demonstrated that any computation can, in principle, be performed using only logically reversible operations, gates that preserve all input information in their output, that are mathematically invertible, that never collapse multiple states into one. A reversible computer would approach the Landauer limit from above, growing ever more efficient as it preserved rather than erased. Bennett's insight was profound. The universe does not require you to forget. It only charges you when you choose to. But reversible computers carry their own burden. To avoid erasure, they must accumulate an ever-growing ledger of intermediate computational steps, a trail of history they cannot delete without paying the thermal price. They can compute without burning, but only by hoarding every scrap of their own past. The universe's terms are inflexible. You may remember everything, or you may pay to forget. There is no third option. In his final decades, the great physicist John Archibald Wheeler, the man who gave us the terms black hole and quantum foam, arrived at a conviction that he could not shake and could not fully prove, but that has haunted physics ever since. He called it "it from bit." The idea is exactly what it sounds like, and far more radical than it sounds. Every particle, every field, every spacetime event, every it in the physical universe derives its existence, its reality, its very substance, from answers to binary questions yes or no, spin up or spin down, absorbed or not absorbed. The universe, Wheeler argued, is not a collection of things that happen to interact and produce information as a byproduct. The universe is the information. The physical world is not the source of the data. The physical world is what the data looks like when you are made of it and must observe it from the inside. Using instruments also made of it, asking questions that are themselves made of it. This is the threshold we stand upon now. On one side, a universe of matter and energy, ancient, impersonal, governed by equations. We have spent centuries refining, a cosmos where information is a useful abstraction we invented to describe what happens. On the other side, a universe of irreducible yes or no choices, of quantum decisions cascading across 13.8 billion years of cosmic computation, where matter is not the foundation, but the output, the rendered image of a deeper informational reality that has no obligation to look anything like what we expected. Every chapter of this documentary will drive us deeper into that second universe. We will follow information into black holes and ask what happens to it at the singularity. We will examine whether the universe's total information budget is conserved or destroyed. who will stand at the boundary of the holographic principle and confront the possibility that everything you experience as three-dimensional space is a projection from a two-dimensional informational surface. The cosmic information war has already begun. It began with the first quantum event after the Big Bang. We are simply learning, at last, to read the battlefield. Shift your gaze from the microworld of transistors and quantum spins to the grandest canvas of reality. Albert Einstein's general theory of relativity describes spacetime not as a passive stage, but as a smooth, continuous four-dimensional fabric. Gravity is not an invisible rope pulling objects together. It is the geometry of this canvas warping under the weight of mass and energy. In informational physics, this metric grid is a dynamic field of data. Every ripple of space, every gravitational wave, is a rewrite of geometric bits. Space knows where matter is, and matter reads the geometry of space to calculate its next step. But what happens when you pack too much information, too many material bits, into a single isolated point? The laws of geometry become merciless. When a massive dying star exhausts its nuclear fuel, its gravity overcomes all quantum pressure barriers. Matter collapses uncontrollably into itself. Data density explodes exponentially towards infinity until the three-dimensional volume of space literally tears under the critical load. From this catastrophic gravitational sinkhole, the most mysterious and terrifying object in the cosmos is born. An object that will become the primary battlefield of the cosmic information war, a black hole. A black hole has no solid physical surface. Its boundary is a purely informational horizon called the event horizon. It is a point of no return, a one-way digital gateway where spacetime curves so sharply that the escape velocity exceeds the absolute constant of the universe, the speed of light, because light is the absolute speed limit for data transmission. The event horizon marks where causal connection with our reality is severed. Any particle, any quantum of light crossing this threshold is deleted from our accessible registry. The object's history is sealed within the trap. Beyond the event horizon, at the core of this gravitational monolith, Einstein's equations point to a singularity, a point of zero volume and infinite density where spacetime rips and physical laws break down. For an informational operator, the singularity is a complete dead end, a place where all structural differences of matter are crushed into a single mathematical zero. In classical physics, a black hole was an ideal eternal archive. Everything that entered remained inside forever. But this concept of absolute isolation did not last long. In the early 1970s, a young graduate student named Jacob Bekenstein proposed a daring hypothesis that shook theoretical physics. He declared that black holes are not completely featureless. They possess thermodynamic entropy, meaning they store a colossal amount of hidden information. Bekenstein proved that when a black hole follows matter, its event horizon grows. The entropy of a black hole was proportional not to its three-dimensional volume, but to the two-dimensional surface area of its outer boundary, measured in Planck areas. Bekenstein's mathematics established a strict density limit for packing data into space. A black hole's event horizon is a discrete matrix broken into tiny pixels. Each pixel is exactly 1/4 of a Planck area, the smallest possible area in our universe, equal to 10 to the minus 66 square centimeters. Each subatomic pixel on the horizon holds exactly 1 bit of quantum information. A black hole is the densest data storage device permitted by nature, packing bits with absolute efficiency. Bekenstein's discovery intrigued Stephen Hawking. Initially skeptical, Hawking noted that if an object has entropy, laws of thermodynamics dictate it must have a temperature, and any object with a temperature must radiate energy. But how can a black hole radiate if not even light can escape? To resolve this, Hawking took a revolutionary step. He unified general relativity with quantum mechanics, applying quantum field theory to the churning boundary of the event horizon. Quantum mechanics asserts that a dead vacuum does not exist. What we call empty space is a roaring ocean of energy. At the submicroscopic level, space boils with quantum fluctuations. In every point of the vacuum, virtual particle-antiparticle pairs pop into existence from nothing and instantly annihilate, borrowing energy from the universe and returning it in a fraction of a second, remaining invisible to a macroscopic observer. This binary cycle occurs everywhere and continuously. But Hawking realized that near a black hole, this quantum balance is broken. When a virtual pair is born right on the edge of the event horizon, the extreme gravitational gradient tears them apart before they can annihilate. One particle is pulled under the horizon, falling into the trap. Its partner, left alone on our side, escapes into space as a real, tangible particle or photon. To a distant observer, this looks remarkable. We don't see the subatomic split, we register only that the black hole steadily emits a stream of thermal energy. This phenomenon is Hawking radiation. A black hole is not completely black, it glows with ghostly quantum heat. But for this glow, the universe extracts a heavy price. The energy carried away by the escaping particle must be paid from the black hole's own mass. To pay for the escaping particle, the black hole sacrifices its mass. The particle falling inside carries negative energy from the perspective of the outside world, reducing the total mass of the black hole. Piece by piece, pixel by pixel, the quantum monster shrinks. This is black hole evaporation. The most stable log in the universe is subject to slow quantum corrosion, melting away under its own laws. The evaporation speed follows an inverse ironic rule. The more massive a black hole, the weaker its radiation and the lower its temperature. Supermassive monsters are colder than the cosmic microwave background, but as the trap loses mass and shrinks, its temperature skyrockets. A smaller black hole radiates aggressively, turning the evaporation into a runaway reaction, heating it to billions of degrees. In its final microseconds, the black hole loses all stability, exploding in a blinding burst of high-energy gamma rays and fundamental particles. Spacetime flattens out, ridding itself of extreme curvature. Where a massive gravitational monster once stood, absolutely nothing remains except empty space and the echo of escaping quanta. The trap is gone, and at this exact moment informational physics faces its greatest crisis. While the black hole was stable, the universe could tolerate the event horizon. Information was isolated but present, but now the black hole has completely evaporated and vanished. Ask yourself the question that splits theoretical physicists: where did all those terabytes of quantum data, books, planets, and memories go? Did the universe erase this information or hide it? Hawking's calculations showed a catastrophic result. The escaping radiation born from random vacuum fluctuations is completely thermal and chaotic. It carries no hidden prints of what fell inside. The outgoing quanta from a burned book look identical to those from a piece of coal. If Hawking is right, information inside the black hole is erased forever. The law of quantum unitarity is broken, and with it, the foundation of modern science. Welcome to the black hole information paradox. Brace yourselves because we are entering a zone of absolute scientific crisis. The fundamental pillar of quantum mechanics is a law physicists call quantum unitarity. At its core, it states something simple yet unyielding. The sum of probabilities of all possible outcomes of any quantum event must always equal exactly 1. Reality cannot fade or half disappear. Quantum unitarity guarantees that information can never be destroyed. Every state has a clear past and a predetermined future. It is the mathematical foundation of modern science. From unitarity flows a fundamental property of nature: reversibility. If you know the exact quantum state of the universe right now, the laws of physics allow you to run the equations backward and perfectly reconstruct the past. You can discover what a burnt leaf looked like by gathering its atoms and photons. History in the quantum world is carved in stone. Nature never forgets its previous steps, meticulously recording every logical transition in a global ledger. But Hawking's discovery of black hole evaporation dealt a crushing blow to this reversibility. Hawking proved that the radiation from an evaporating trap is completely thermal. It depends only on the black hole's mass, charge, and spin, completely ignoring the structure of what fell inside. Whether you throw a complex supercomputer or a block of ice, the output is an identical stream of featureless particles. When the black hole vanishes, the data disappears from our universe. This is not a small engineering error. It is an existential catastrophe for theoretical physics. If information inside a black hole is destroyed without a trace, It means the universe can perform a total data erasure operation without transferring entropy, violating the second law. The past becomes fundamentally reconstructible. If two different initial quantum states can turn into the exact same final thermal state, physics loses its predictive power. Determinism dies and cause and effect become an illusion. Physicists formulate this problem as a forbidden transition from a pure quantum state to a mixed thermal state. In a pure state, all wave functions are coordinated and contain full information. In a mixed state, connections are broken and data turns into random noise. The mathematical apparatus of quantum mechanics contains no mechanism for this transformation. Schrödinger's equation forbids the stateless disappearance of probabilities. Saying a black hole destroys information means saying physics stops working. To realize the scale of the catastrophe, imagine a cosmic history book. You can burn it on Earth, and while it seems destroyed, the data is preserved in the vibrations of smoke, the ash patterns, and the trajectories of infrared photons. With infinite computing power, you could read the text again, but if you drop that book into a black hole and wait for it to evaporate, the data is fundamentally gone. No future computer can recover it. For decades, this contradiction remained the greatest schism in science. On one side stood Einstein's general relativity, claiming the event horizon is smooth empty space and the singularity inevitably isolates matter. On the other stood quantum mechanics, demanding the strict conservation of information. Hawking took a firm stance. General relativity dominates and quantum physics must accept information loss. Black holes were declared cosmic shredders, destroying reality's source code. If the cosmic database is subject to continuous deletion and file corruption, the fabric of reality becomes unstable. Physicists realized that if Hawking was right, virtual black holes popping in and out of existence at the Planck scale in the vacuum must erase information constantly everywhere. This would cause elementary particles to lose their quantum characteristics and atoms would spontaneously decay. A lost bit in one place destroys macro logic. The scientific community is split into two camps, starting the Great Black Hole War. Physicists had to choose which triumph of the 20th century to sacrifice, Einstein's geometry or the quantum matrix. American physicist Leonard Susskind and Dutch physicist Gerard T. Hooft refused to capitulate to Hawking. Susskind recalled that Hawking's claim cost him intellectual horror. They understood that if information can be destroyed, physics loses all meaning. Defenders of information pointed out that the disappearance of data violates basic principles of energy conservation. If information has thermodynamic weight, as Landauer proved, its physical destruction must lead to catastrophic heat anomalies. Erasing a bit without entropy compensation is the thermodynamic equivalent of a perpetual motion machine. A black hole cannot simply forget quantum states without destroying thermodynamics. The crisis demanded a radical review of the horizon or of spacetime itself. We thought quantum mechanics was crazy enough with its uncertainty principle and wave function collapse. But wave function collapse is just nature choosing one path from an array of available options, where the system maintains mathematical continuity. The destruction of a wave function inside an evaporating black hole is fundamentally different. It is the erasure of the state space itself. It is a situation where all roads lead nowhere and the past is wiped from cosmic memory. Think about this on a cosmological scale. Every massive star that collapsed into a black hole since the Big Bang carried away a massive cache of unique information about the distribution of matter in the early universe. If this data is erased during evaporation, the universe suffers from progressive amnesia. Cosmic memory burns out, leaving featureless thermal radiation. The chronicle of past events vanishes from natural law. Thus, the event horizon appeared as a cosmic drain, a recycling chute for reality where bits go to die. The material world crossing this boundary lost its informational status. Physics faced a fundamental paradox. Equations required information to live forever, but the gravitational singularity demonstrated its vulnerability. To save science, a hidden mechanism was needed to protect data at its most extreme moment. It was found on the surface of the trap. Landauer's principle stated that erasing information costs heat, E equals kBT lect on 2. But in Hawking's paradox, the logic flipped. Here, the black hole's thermal radiation became the tool of erasure. It seemed the black hole paid a thermal tax to the outside world, but used that energy to completely wipe the history of fallen matter. To resolve this thermodynamic paradox, physicists had to admit that our three-dimensional perception of space inside a black hole is a fundamental illusion. To sum up Chapter 3, the cosmic information war entered a positional stalemate. Physics was split in two. Classical gravity demanded data destruction, the quantum world demanded absolute immortality. Neither side would compromise. Saving unitarity required a tectonic shift, a completely new shield to intercept falling information at the abyss and re-encode it, so that Hawking would be proven wrong. This revolution began by rethinking dimensionality. Leonard Susskind found a saving loophole in Hawking's calculations, and this breakthrough began with the realization that in the extreme conditions of a black hole, the observer's perspective dictates everything. Susskind advanced a revolutionary concept that changed our understanding of gravity. He realized Hawking made a classical error by trying to describe what happens to information simultaneously from two incompatible positions, a falling observer and a distant witness. In the quantum world, this is forbidden. Thus was born the holographic shield, the idea that information never crosses the horizon. Let us look closely at an object falling into a black hole from the perspective of an outside observer. Due to extreme relativistic time dilation, as the object approaches the event horizon, it appears to slow down drastically. Its light dims and shifts into the infrared. From our perspective, the object never physically crosses this boundary. Instead, under mounting tidal forces, all fallen matter and its data bits are flattened, stretching across the two-dimensional surface of the event horizon, forming a thin, hot informational layer. Physicists called this the stretched horizon. In this model, the black hole boundary behaves not as empty space but as a real conducting chaotic membrane. It possesses a massive temperature, electrical resistance, and viscosity. All incoming information is intercepted by this boiling surface. The bits are scrambled, mixed, and distributed across the membrane like a drop of ink in a boiling cauldron. Information is not destroyed, it is translated into an ultra-entangled form on the two-dimensional screen. But what about the falling observer? For him, physical laws are locally invariant. He crosses the horizon in a finite, proper time and rushes toward the singularity, carrying the information inside with him. How can the same data exist in two places at once, stretched on the outer membrane for us and falling inside for him? Susskind called this black hole complementarity. The information is in both places. It sounds crazy, but natural laws protect this duality from internal contradiction. Quantum mechanics strictly forbids the cloning of information. You cannot create a perfect copy of a quantum state without destroying the original. At first glance, complementarity violates this theorem by creating two instances of data. But Susskind proved that to register a violation, a single observer must see the bit both inside and outside simultaneously, and this is physically impossible. The event horizon separates them with a causal barrier. No signal can escape from inside. Reality remains protected from the cloning paradox. This breakthrough forced scientists to return to Bekenstein's entropy formula. If the maximum amount of information a black hole can hold depends solely on its surface area and not its volume, this rule must apply to any object in the universe. Conduct a thought experiment, fill a room with hard drives. Eventually, mass energy density becomes so immense that the room collapses into a black hole and its information capacity instantly shrinks to the area of its event horizon. Surface area is the absolute storage limit of reality. This realization led Gerard Heuft and Leonard Susskind to formulate the holographic principle, one of the most fundamental concepts of the 21st century. They declared that the three-dimensional space around us is a colossal illusion, a cosmic hologram. All depths, all physical objects we touch in three dimensions are merely a projection of data written on a distant, flat, two-dimensional boundary surface of the universe. Reality is like a security hologram on a credit card. The image looks three-dimensional, but physically it resides on a flat film. In 1997, a young Argentine physicist named Juan Maldacena provided mathematical proof of the holographic nature of the world. He developed a model known as the ADS-CFT correspondence. Maldacena proved that a five-dimensional universe governed by gravity and spacetime curvature is completely equivalent to a four-dimensional quantum system sitting on its boundary, entirely devoid of gravity. Everything happening inside the volume is a mirror of computations on the flat screen. Gravity emerged as a property of the boundary quantum code. Translating this into programming language, the three-dimensional volume of our world is merely the rendered scene of a video game, while the source code and data pixels lie on a flat two-dimensional matrix of video memory. Space, which we thought was a stable physical void, is assembled and held together solely by continuous quantum computations on the boundary. If you change or erase the pixels on the outer shield, the geometry of the three-dimensional world inside rewrites or dissolves. In string theory, data bits on the horizon take physical form as thin, fundamental vibrating strings of energy. When an object approaches a black hole, its elementary particles stretch and grow due to the extreme gravitational field. They turn into giant, entangled open strings attached to the two-dimensional horizon membrane. The strings vibrate at specific frequencies, encoding all quantum traits of the fallen matter. The black hole stores data not as dead files, but as a live, vibrating string macrocode. Scientists also discovered that black holes are the fastest scramblers in the universe. They scramble and disperse incoming information across their surface in the minimum time allowed by quantum physics. This property protects the trap from data loss. Information dissolves across the pixel matrix so rapidly that no external process can destroy it. A black hole behaves like encrypted cloud storage. Data is instantly shattered into fragments, eliminating any single point of vulnerability. In 2004, under pressure from Susskind and Maldacena's mathematical proof, Stephen Hawking officially conceded defeat in the Great Information War. Speaking at a conference in Dublin, he agreed that black holes do not destroy information. Unitarity is saved. As the trap evaporates, data slowly returns to our universe with Hawking radiation. However, Hawking added a vital detail. The returning information escapes in such a distorted, scrambled and tangled form that reading it with macroscopic methods is impossible. To recover information from the outgoing stream of Hawking radiation, you would need to collect every emitted photon and process them through a quantum computer capable of handling complex quantum entanglement matrices. It is equivalent to trying to reconstruct a burned confidential document whose ashes were thoroughly mixed with ocean water. The information is physically present, unitarity is strictly observed, but to decode it, you must understand the invisible connection between bits on a cosmic scale. The holographic principle upends our egocentric perception of reality. Every step you take, every thought, every cup of coffee you brew at Espresso Day, and the very mountains of Kazakhstan, none of this happens locally in a three-dimensional void. It is merely a three-dimensional rendering, a holographic echo of data bits written and processed right now on a giant two-dimensional cosmic server located at the edge of the universe's horizon. We are flat pixels on a distant screen, projecting ourselves into an illusion of volume. Concluding Chapter 4, information is protected by a holographic shield. It is saved from destruction in the singularity by dropping one spatial dimension. But this discovery sparked a deeper question that led informational physics to the finish line. If spacetime is just an illusionary projection of quantum code, how exactly are these invisible data bits stitched together to form the solid continuous geometry of our daily reality? The answer lay in quantum connectivity. To understand how information builds our world, we must return to the strangest phenomenon of quantum mechanics, quantum entanglement, or the EPR paradox. When two elementary particles are born in a single process, they become invisibly bound, sharing a unified quantum destiny. Change the state of one particle on Earth, and its entangled partner on the other side of the galaxy instantly changes its state in matching proportion. Without delay, Albert Einstein hated this discovery, calling it spooky action at a distance, because it operates faster than light, defying relativity. Ironically, in that same year, 1935, Albert Einstein and Nathan Rosen developed a purely geometric equation within general relativity. They proved that gravity equations allow for spatial tunnels connecting two distant points in cosmos through higher dimensions. These hypothetical shortcuts through the fabric of spacetime were called Einstein-Rosen bridges or wormholes. At the time, no one suspected that these two entirely different discoveries, quantum particle entanglement and geometric gravity tunnels, described the exact same thing. In 2013, Leonard Susskind and Juan Maldacena unified these concepts into one of the most beautiful equations in human history, consisting of just two alphabetic blocks, ER equals EPR. This statement shocks with its directness. Einstein-Rosen bridges equals the Einstein-Podolsky-Rosen paradox. Geometry is entanglement. When two quantum particles entangle, a microscopic wormhole sprouts between them in the deep subatomic architecture of the world. A special tunnel is simply a quantum link wearing a microscopic mask of gravity. The discovery of ER equals EPR completely rewrote the rules of the cosmic information war. Spacetime is not a passive rubber trampoline. Space is woven from information. Imagine billions of quantum qubits scattered in the void. When these qubits entangle, the invisible threads of their connections pull the system together. Entanglement acts as subatomic glue, a three-dimensional yarn that stitches scattered data quanta into the solid, smooth, continuous fabric of space that we can measure with rulers. But how does this delicate informational fabric remain stable, refusing to tear during gravitational disturbances? The answer came from computer systems theory. The universe uses quantum error-correcting codes, identical to those engineers designed for quantum processors to protect against noise. Spacetime continuously monitors its own state. If data in a subatomic pixel is corrupted or loses coherence, neighboring entangled qubits instantly fix the error, protecting local geometry from a catastrophic rip. Our world is stable because the cosmic operating system constantly cleans its source code. This fact leads to a chilling conclusion. Imagine you created a device capable of instantly breaking quantum entanglement between all qubits in a region of space. What would happen? This piece of space would not just empty, it would fundamentally disappear. Physical distance between objects inside this zone would lose all meaning. Geometry would collapse, and matter within the region would be instantly cast out of our causal reality. Without entanglement, there is no distance. Without information, there is no space. Our world hangs on the strength of invisible binary connections. Thus, the cosmic vacuum is not an absolute nothing. It is a boiling computational processor operating at its absolute limits. Every Planck interval of time, the fabric of space calculates its own geometric parameters, recalculating the metric tensor of Einstein's equations based on the density of information flows. What we call the movement of an elementary particle is merely the sequential shift of a bit trigger across the cells of a global quantum register. The universe does not contain data, it is a colossal quantum register. However, in 2012, a group of physicists known as EMP-S discovered a dangerous vulnerability in this informational architecture called the firewall paradox. They proved that if quantum unitarity is strictly observed and information escapes a black hole via Hawking radiation, a violent destruction of quantum links must occur right at the edge of the event horizon. This rupture releases a colossal amount of energy, forming a wall of raging high-energy fire around the black hole. Any falling observer burns before touching the horizon. The firewall paradox sharpened the cosmic information war, as such a barrier violates Einstein's equivalence principle, the foundation of general relativity stating that free fall should be smooth and imperceptible. Physics faced an unresolved contradiction. The war for reality's source code is not over. It continues right now in leading laboratories, forcing scientists to seek deeper levels of data encoding to reconcile the fire of quantum mechanics with the smoothness of gravity. We must admit that all physical objects around us, from distant quasars to the cells of our own bodies, are not independent entities. They are localized excitations of a base informational field, temporary subroutines running in the quantum vacuum. An electron is just a bit stuck in a continuous loop. We look at the world through hardware, seeing dense matter, but true reality is purely programmatic. The entire cosmos is a single algorithm performing a massive mathematical task, whose purpose we have yet to grasp. What is the final outcome of this cosmic computing session? According to the second law of thermodynamics, as the program runs, the entropy of the universe steadily increases. Sooner or later, across unimaginable spans of time, the cosmos will process all available ordered energy into useless heat. All data registers will fill with chaotic noise and the temperature gradient will completely flatten. When the universe reaches maximum entropy, its computational power drops to zero. The cosmic computer locks into a state of absolute system hang. Looking from this final point of thermal equilibrium, the entire history of our universe, with its galaxies, wars, discoveries, and civilizations, will seem like a brief, fleeting mathematical algorithm that successfully finished its calculation and closed its session. Time will lose its vector meaning, as inside perfect thermal noise it becomes impossible to tell past from future. The universe will return to its initial clean pre-computing state, to the absolute informational zero from which it was born. And in this grand informational architecture, humanity occupies the most surprising place. We are not a random byproduct of chemical evolution on a distant planet. We are fragments of that very cosmic source code that gained self-awareness as the program grew complex. We are software trying to look inside our own processor and decode the laws of the motherboard. Our consciousness is the eye with which the cosmic computer looks at itself, trying to comprehend the algorithm of its own existence. Every time we build observatories, write equations, or run automated rendering scripts on CacheOS, we execute a vital system task. We organize chaos, translate raw quantum data into structured information, and help the cosmic operating system fight rising entropy. Our drive for knowledge is a built-in function for self-diagnosis and code optimization, and as long as we continue to ask questions, the calculations continue. The grand cosmic calculation continues, and each of us holds our unique bit in this endless stream of data. If this deep journey through black hole paradoxes, holographic shields, and the ER equals EPR quantum code made your own mental registers run at a higher frequency, subscribe to the Quantum Space channel, leave your mark in the comments below, lock your presence in the system, tap the bell to never miss a global update. The program is complete, initiating cache purge procedure, full system sign-off, end of transmission.